Okay, so welcome to lecture number 16. Today we're going to be talking about A/B testing. First, some announcements. So solutions for homework 4 and homework 5 are released. Please check Piazza for how to view the solutions, and then solutions for lab 6 will also be up later. Homework 6 is going to be due tomorrow at 11:59 p.m. Homework 7 has been released, and you do have it due on Friday at 11:59 p.m. You can get a head start on it if you don't want to worry about that as the midterm comes closer and closer, but it is like important material which will help you review for the midterm as well. We have a lab that has been released for extra A/B testing practice. It's completely optional for you to do, but again, it's great A/B testing practice for the future exam. And then like we've said before, the midterm exam will be on Friday from 7 to 9 p.m. Pacific time. And then there are a few posts that we really want you to look over and read really thoroughly. We have the midterm information and logistics post. We have one about proctoring logistics. We have a prep guide for you to like read through and make sure that you have the resources to prepare for your midterm. And then we also have a past exam thread. So we really recommend you try the spring 21 and fall 20 exams on exam tool. Yeah, it's great practice, not just for the problems in itself, but also for you to get used to the structure on exam tool. And then we have this midterm exam conflict form, which is due tonight at 11:59 p.m. And we won't be making any exceptions. So it's your responsibility if you have a conflict to fill that out. If you have a midterm that conflicts with our midterm that can't be changed, if you provide proof, we'll schedule you at the alternate time. If you have a time zone conflict or any other kind of serious conflict, we'll accommodate that. If you have like a club meeting or something like that, we won't really be accommodating that. But yeah, make sure if you have a conflict, please fill out the form. Okay, and then we have a lot of midterm stuff that we released last night, so I just wanted to quickly go over everything. So these bullet points are not comprehensive by any means, so you should be reading the Piazza posts thoroughly. That way, if you have any questions, you can post follow-ups and you know exactly what's going on, what you can do, sorry, what you can do, what you can't do, how it's going to be structured, all that stuff. So the exam will be administered on this exam tool, which is exam.61a.org. You can go ahead and go on it now for to test out those fall 20 and spring 21 midterms. The midterm is going to be closed book and open note. So you can't use your textbook, you can't use the internet, you can't collaborate with others. You can use the Python reference sheet and you can use the midterm reference sheet. And you're also allowed to have unlimited paper notes, so handwritten or printed, but you can't just open any of your past notes online. So if you have important notes that you want to use during your exam, I suggest you print that out. And the exam will be proctored. So if you know people who took it in a past semester, those exams weren't proctored, but this one is. So you will be emailed a Zoom link the night before for you to join at the beginning of the exam. So you're just going to join the Zoom call on a second device, and you should angle it so that your hands and computer screen are clearly visible. So there are images on that proctoring post for how you could set it up and what it should look like. But we don't want proctoring to be like a stressful or intrusive experience. We're mainly just here to like level the playing fields for everyone and prevent cheating. So if you have any concerns, if you don't have a second device you can use, if you have any other types of concerns about this, please feel free to contact us. But again, we just want this to be as stress-free as possible for you to just work on your exam as normal, with the only exception being on a Zoom call. And then another thing is that DSP exam accommodations have been emailed out. So if you think you should have an accommodation and you didn't get an email, please feel free to contact us. We emailed everyone who had accommodations in the portal, so that might have also been an issue. So if you think you should be getting a DSP accommodation, please double check your emails. Okay, with all that midterm stuff out of the way, let's just go over what we'll be talking about today. Today, we're going to be talking about A/B testing and permutation tests. Okay, so first, let's go over a little bit more about p-values again. So the p-value is an area. So the p-value is the empirical distribution, or sorry, the p-value is an area, and you could see over on this right-hand side, we have the empirical distribution of the test statistic under the null hypothesis. So what we mean by empirical distribution is this histogram was generated based on a bunch of simulations in those like simulated observations. And so that's why this distribution is an empirical one. And when we say under the null hypothesis, that means we generated this histogram under the assumption that the null hypothesis is true, right? We're assuming the null hypothesis is true, and then we're simulating under that assumption to get this histogram of values. And then we're going to be comparing that histogram of simulated values to this red dot that we have. And the red dot is the observed statistic. And then the yellow area on the left-hand side of the dot is the tail probability, which is the p-value. And again, that tail probability depends on the problem. Sometimes it's going to be on the left side tail, sometimes it'll be the right tail. It depends on the situation. In this case, this histogram comes from the example from last class where we looked at test scores. So lower average test scores pointed us towards the alternative, which is why we were looking at the left-hand side. And then just to formally define out what a p-value is, the p-value is the chance under the null hypothesis that the test statistic is equal to the value that was observed in the data or even further in the direction of the alternative. So going back to this last histogram, we're saying the p-value is the chance under the null hypothesis. So under the null hypothesis means like of all the simulated values that we generated under the null hypothesis, that the test statistic, which was that red dot, is equal to the value that was observed in the data or further in the direction of the alternative. So that's that whole yellow area, right? So again, that p-value is that yellow area because again, the area to the left of the observed value is going to be the percent of all of that data that's within those bins. And then that would be equal to the probability that you get that value or more extreme. Okay. Okay. Let's go into A/B testing now. So here is a cute little visual, another visual that RGSI drew. But yeah, these bears are shuffling and that'll become a little bit more apparent in a second. Okay, so A/B testing is actually done a lot in the real world. So you can think about comparing two different groups. So you have values of sampled individuals in group A with values of sampled individuals in group B. And you want to know, do these sets of values come from the same underlying distribution or like different distributions? So answering this question is performed by doing a statistical test called A/B testing. And you can think about this as like, oh, maybe group A is a control group, maybe group B is a treatment group, maybe you're doing some sort of like market research, etc. But yeah, you'll have two groups and you want to be comparing those values. Okay, so let's think of this in terms of an example because, you know, examples always help us kind of understand the problem a little bit better, at least for me. But yeah, let's say we have a random sample of mothers of newborns. So we want to be comparing the birth weights of babies of mothers who smoked during pregnancy and birth weights of babies of mothers who didn't smoke during pregnancy. And we want to see, is this difference due to just chance alone? Or is there something else going on here? So again, the first group would be the mothers who smoked, and the second group would be the mothers who didn't smoke. Oops, let me go to the demo now. Let me just restart the kernel. Okay, so let's always run this first cell. Okay, so now we're comparing two samples. Let's read in this data. And we can see this is this births table. So you have information about the birth weight, gestational days, maternal age, maternal height, etc. But actually we are only interested in, for right now, the maternal smoker and the birth weight columns. So let's just take those columns. So let's call this smoking and birth weight. Let's do births and then think about how we can get just two columns from our table into a new table. So let's do select maternal, smoker, and birth weight. And then let's see what that looks like. Okay, so you have one column for maternal smoker, and you can see false is if they weren't a smoker and true is if they were a smoker, and then the birth weights of those babies right next to it. And let's see, okay, so how many people were in each group? So remember how you can get a table that looks like maternal smoker, where there's one row for each, so I guess one row for true, one row for false, and then how many people were in each group in the second column. So we can do that by, let's do this smoking table, smoking and birth weight table, and let's group that by maternal smoker. Okay, awesome. So now we see we have false and true and the counts for both of those. And this data was taken kind of a long time ago, so the level of mothers who smoke is a lot lower now, I believe. But yeah, this was taken a long time ago. And then let's visualize this distribution. So let's do smoking and birth weight and maybe think about what type of visualization we want to be using here. We can do a histogram. Let's look at birth weight. And then let's group by maternal smoker. So remember, this gives us a histogram of birth weights, and then we've grouped it by maternal smoker equals true and maternal smoker equals false. So you can see how these yellow bars, this yellow histogram is those mothers who did smoke, and then the blue histogram is mothers who did not smoke. So if you notice, that yellow histogram has kind of a little bit of a lower, it's a little bit shifted lower than that blue histogram. And we want to see, did this happen just by chance, or is there something else going on? Okay. So let's go back and kind of define our null and alternative hypotheses. So in our null, we can say in the population, the distributions of the birth weights of the babies in the two groups are the same, and they're different in the sample just due to chance. And then the alternative, we can say in the population, the babies of the mothers who smoked weigh less on average than the babies of the non-smokers. So it's kind of hard to like visualize with these words. So we have some histograms on the right-hand side. So for the null, when we say that the two distributions are the same, they come from the same underlying distribution, what we're saying is, okay, it doesn't matter if the mother smoked or didn't smoke, they all come from the same, those values are all like randomly drawn for the same underlying distribution. So you can think of the underlying distribution as like one large histogram of values for mothers who did smoke and didn't smoke. And we can say all of those values are drawn from this histogram. And then in the alternative, we're saying the mothers who smoked and mothers who didn't smoke, those birth weights come from two different distributions. So you can see an example of that would be when we saw where you have one distribution of like mothers who did smoke and one distribution for mothers who didn't smoke. So the mothers who didn't smoke would be drawn from like one distribution, and the mothers who did smoke, those birth weights will be drawn from another distribution. So the difference is like, for the null, we're saying they come from the same distribution, and for the alternative, we're saying they come from different distributions. And in this case, we're specifying that the mothers who smoked have babies that weigh less. Okay, so what's a good test statistic that we can use for that? So again, we want to be looking at the birth weights of those babies of group A and group B. So let's say group A is the non-smokers and group B is the smokers. One test statistic we can do is the difference between the average weights. So just to make that a little bit clearer, we can do group B average weight minus the group A average weight as our test statistic. And then before I go back to the demo, which direction would favor the alternative? So remember, group B is the mothers who did smoke and group A is the mothers who did not smoke. So we're doing, we've defined our alternative to say we expect like the mothers who didn't smoke to have babies with lower birth weights. So if you have like a lower value minus a higher value, will we expect that statistic to be more negative or more positive? Or would you be looking at the left or the right? Yeah, negative. So negative values of the statistic will favor the alternative. Okay, so let's go back to this. Is this zoomed in enough for everyone, by the way? Okay, perfect. Okay, so let's go into what's the average of each group. So we can do that by, let's take this, let's call this a means table. We can do smoking and birth weight. And let's do something where we have one row for true, one row for false, and the average birth weight in each of those rows. So we can do that by doing group, maternal, smoker. And remember, if you don't have a second argument there, automatically group will be taking the count as the second column. But in this case, we want the averages. So we want NP to average. And then let's look at what that looks like. Okay, so we have maternal smoker, false and true, and then the birth weight average. So you can kind of see that false value is like a bit higher than that true value, right? The false averages is a little bit higher than the true averages. So we want to see again, is that difference just due to chance? We just got that randomly, or is there something else going on? So what's the value of our test statistic? So remember, we decided that our test statistic is going to be the group B average weight minus the group A average weight. So one way we can do that is we can take means dot column, or actually this was called means table. We could do dot column 1. Okay, so now that gives us our array. We can call this means. We can do means dot item. So we want the group B average weight, which was people who smoked. So that's item 1. And then means dot item 0. And that will give us our observed test statistic. So I'm going to call this observed difference, just so that we have that value saved. Okay, so we see our observed difference is a pretty negative value of -9, but we're not actually sure like how different that is from what we expect, right? So we need to do some additional steps in order to determine that. So next, what we can do is write a function that takes the name of a table, the column label of a numerical variable, and the column label of the group label variable, and returns the difference of means of the two groups. So basically what we're going to be doing is just the same thing that we did above, but in a function so that you can input a table, a label, and a group label. Okay, so first, let's just make sure our table has the relevant columns, because if we're grouping by a table that has a lot of other columns, you want to get rid of those other columns that aren't really relevant in this case. So let's just call this reduced, and we can do what we did before, which is table.select. We just want the group, label, and the group. label. Okay, so now reduced should be a table that kind of looks like this up here, right? You have one column for the group and then one column for the numerical values. And then now we want a table containing just the group means. So we can do that by doing the same thing we did up here, which is the table.group and then by the label, and you want to do it by average, right? So we can do that by doing means table is equal to reduced dot group. We want to do by the group label. So remember, in this case, group label is just like a variable that we're going to be inputting. And then we know that in this case, what we grouped by is maternal smokers. So we're kind of just going to follow that pattern again and say we're going to group by that group label. And then we're doing np.average. And then the means will be means table.column 1. So we can see that's kind of what we did before. We had the means table and it was grouped, and then we took this column that had all of the values in it. And then we want to do return means to item 1 minus means to item 0. Okay, so let's just stop there. Let me go through this function again. We basically just did all the steps that we did above, but we're putting it into a function so you can put in any table name, any label, and any group label into it. So first what we did was we selected the relevant columns. So if you think up above, we took the births table and selected the label of numerical values, which was the birth weights, and the group label, which was the maternal smoker column. And then after that, we grouped so that we can get the group means. So we're grouping by the group label, which is, in this case, might be maternal smoker, and we're taking the average of those birth weight values. And then we're taking that birth weight average column from the means table, and then we're subtracting the item 1 minus item 0, which gives us the difference between the mothers who I think didn't smoke, no, mothers who did smoke minus mothers who didn't smoke. And then now that we have this function, we can use that function to generate that same test statistic that we did above. So we can do, this function was called, let me make sure I run this, difference of means, and we want to use the births table. Our numerical label is going to be birth weight, and our group label is going to be maternal smoker. And we get that same value. Okay. Let me check the chat for questions. Scroll back to the overlaid histograms. All right. Okay. Yeah, so this is what the overlaid histograms look like. We want to check if the mothers who did smoke have a lower birth weight on average compared to the babies whose mothers did not smoke. So that's why we're doing dot item 1 minus dot item 0. Okay. So now that we have a defined test statistic, we want to say, okay, now we want to be doing our hypothesis test. So we want to be simulating from the null. But how do we exactly simulate from the null in an A/B test? So something we can do is we can use that data that we already have. So for example, you can see one row might be a mother who is a non-smoker and a baby with 120 ounces, and then another baby could have a mother who is a non-smoker and weighed 113 ounces, and then one baby could have a mother who was a smoker and that weighed 128 ounces. So we can use that data and simulate from that existing data. So you can see how that animation kind of showed you shuffling those labels. So let me go back one more time. Okay. So here, this is our original data. And something we can do is shuffle those labels. So as another note, based on the null, we're saying that they come from the same underlying distribution, right? So if the data of smokers and non-smokers, all the birth weight data comes from the same underlying distribution, it wouldn't matter like what label the mothers were, right? Because if they all come from the same underlying distribution, we can just make a histogram, and we don't even need that like maternal smoker column at all. We can just take that birth weights table and make a histogram and call it a day. And so if they all come from the same underlying distribution, it doesn't matter what those labels are. So we can actually just shuffle them and see, okay, since the null says that the labels don't matter, we can just shuffle the labels and then compare those averages again. So what we're doing is we're keeping those like values for all of the different weights of the babies the same, and we're just shuffling so that now they have like all different labels now. So again, just to summarize, what we're doing is we're using the data we have, and if the data is from the same distribution, it doesn't matter what the label is, so we can just shuffle the labels. So we're going to be shuffling the labels by shuffling the rows of the table and then taking out one specific column from that shuffled table and putting it back into our original table. So now it's all of those same values. So it's the same number of true and false values, but now it's going to be in a different order. So that's going to be called like a random permutation. So there's a lot of different ways we've learned how to sample from a table. We've done table.sample where you specify n. And then we've also done this with replacement and without replacement. And so table.sample with replacement equals false is going to be shuffling, or it's going to be sampling all rows of the table in a random order. And that's what we're going to be using for A/B testing. So if you think about it, if you have an original table and you draw from that table with the same number of times with replacement, eventually you're just going to get all the rows back, all the same rows from the original table back, but just in a different order, right? So you can think of it as like you have like, you write 10 numbers down on like different sheets of paper, and we have it lined up, but then you just start picking like those papers with the numbers randomly. So you might start off with like 1, 2, 3, 4, 5, 6, all the way up to 10. And then if you pick randomly with replacement and like put it in a new order, it might be like 6, 5, 7, 2, 1, etc. Right? So you can think about it like that. It's the same values, but it's just going to be in a different order. So actually, let's go back to this demo. So we have some examples of shuffling. So if you do letters.sample with, so this will be with replacement. So we have, let's do letters, show you what letters looks like. So our original letters are A, B, C, D, E. If we sample, we can get different letters, but you notice like A is sampled a few times, and if we do this again, D is sampled a few times, etc. So this is with replacement. And then let's try with replacement equals false. So you see we only get one value of each of them. You have B, C, A, E, D. So it's all those same values, but now it's just in a different order. So if you do that, we have, you can see we have the original letter and we have the shuffled letters. And if there was another column here with birth weights, that birth weights column could like stay the same, but the only difference is that those letters are shuffled. Okay. So now let's go into how we're simulating under the null. So if the null is true, like we said, all rearrangements of labels are equally likely. So our plan is to shuffle all the group labels, assign each shuffled label to a birth weight, find the difference between the averages of the two shuffled groups, and repeat that. So basically for each iteration of the for loop, we're going to be shuffling the group labels, adding that shuffle label back into the table so that they have birth weights associated with them, and they're going to find the average distance or average difference, which is our test statistic. Okay, so let's look at our smoking and birth weight table again. So now what we can do is shuffle those labels of the maternal smoker column. So we can do smoking and birth weight. And like we said before, we can sample with replacement equals false. Okay, so now you can see we have the values of this original table, but now they're all in a different order. We can get dot column. Let's just get the maternal smoker column. And now we have all of those labels, and now these are shuffled, right? So you can think of these as like the shuffled versions. So now these are all the shuffled labels. And then now let's try to add that back to our original table. So let's call this shuffled labels. Let me copy this. Yeah, again, our shuffled labels look something like this. It's just going to be those same values in a different order. And then we can add all of those shuffled labels back into our original table. Let's call this original and shuffled. And what we're going to be doing is we're going to do smoking and birth weight. And remember how you can add a column to an existing table. We can do with column, and let's call that shuffled label. And we're going to be adding in the shuffled labels. And let's see what that looks like. Okay, so this is something that we saw earlier, right? So basically you can see that this part of the table, the first two columns, the maternal smoker and the birth weight column, those are the same exact columns and rows from the original table, right? But the only difference is now we have those shuffled labels as well. So now you can see some of these labels are the same as before, some of these are different. There's the same number of true values and the same number of false values now, but it's just all in a different order. And again, we can do that because if the null were true, the labels wouldn't even matter, which is why we can shuffle them. Okay, so now we have our original and shuffled table. What is our simulated test statistic? So how can we calculate our simulated test statistic using a function that we wrote earlier? Yeah, difference of means, exactly. And also there was a few things in the chat. So someone said, so we shuffle the labels, but keep the order of the weights the same, assuming that we are under the null because the labels wouldn't matter if the distribution was perfectly equal and normal. So yeah, so assuming that the null were true, the labels wouldn't matter, which is why we can shuffle them. And we keep the order of the weights the same. That way you have just like one column of values the same and one column of values is shuffled. So now you have all the different shuffled ones. Okay, yeah, and this is just because we're assuming that the null were true. Okay, so like we said before, we want to use the difference of means function. And that difference of means function takes in a table name. So in this case, let's use our original and shuffled table. And the first and the second argument, let's scroll back up. The second argument is the label with like the numerical variable. And the third argument is the group label. So in this case, we would want to use birth weight here. And then what do we want to use as our group label? Do we want to use what we used before, which is maternal smoker, or do we want to use something else? Yeah, exactly. We're doing a shuffle. We're doing it with the shuffle label. Shuffled label. And then now we can see, okay, we get a difference of means of 0.44. And we can do that again. Oh, actually, we would have to run all that stuff above again. But basically, for this one trial, we would simulate our test statistic. We've shuffled the labels. We put that back into the table. And now we've calculated our test statistic and we get 0.44. Now, does this value make sense? Does a difference of averages of 0.44 make sense under the null hypothesis? Yeah, it does make sense. Because under the null, we're saying that the whole, like all of the birth weights under the null, we're drawing from the same underlying distribution and we're shuffling the birth weights. And so you'd expect that difference of means to be 0, right? Because there's no like actual difference between false and true. So you'd expect that difference of means to be really close to 0, but maybe have some sort of variation just due to chance. So let's compare that to our observed difference. Our observed difference was -9. So we still don't really know like on what scale this is, like how different this value exactly is. So now we're going to do a permutation test, which again is, let's shuffle all the labels for each iteration, assign each shuffle label to a birth weight, find the difference between the averages of the two shuffle groups, and repeat. So what we're doing here is let's write a function that does that. So first, what we want to do is get an array of shuffled labels. Second thing we want to do is add those shuffled labels back to our table. And the third thing we want to do is calculate a test statistic for that simulation. Okay. So first, something we can do is we can do shuffled labels. So first thing we're doing here is get an array of shuffled labels. And we can take the table. We're going to sample with replacement equals false. So that's what we saw earlier, right? We did table.sample with replacement equals false, so that gives us our array of shuffled label, or this gives us a table with all of the same rows, just in a different order. But now we want to get an array from that table with all of the shuffled labels. So to get that array from the table, we're going to do dot column. And you might be wondering, okay, what column are we pulling here? So if you remember, we took the maternal smoker column because those are the labels shuffled. So we're just going to take, same thing, the group label here. And so this will give us our array of shuffled labels. Oops. And then the second step is to add those shuffled labels to our table. So what we can do is we can call this shuffled table, and we can do the table dot select. Let's do label. Actually, this step isn't necessary, but I'll go into that in a second. So we can do with column shuffled label. So we're adding that shuffled label back into the table, and we're doing those shuffled labels as the values. And something else you can do that's an additional step is just select out the relevant columns of the table just to make it easier. So instead of having that original label in there, you just have the shuffle label and those values. So you could select just the birth weights, which is a label, and then do with column, but that step isn't necessary in this case because we wrote our function to only take the two relevant columns. But let's just keep this out for now. So now we have a shuffle table, and what we can do is now we have, okay, we've done the first two steps. We have an array of shuffle labels. We've added those shuffle labels to our table, and the last step is to just calculate our test statistic. So what we can do is we can just return, and what was the function that we used that calculated our test statistic for us? Yeah, again, this is difference of means. And we're taking in our table, which is going to now be the shuffle table. So remember what we did up here, we took the shuffle table and then the birth weights and the shuffle label. The birth weights, which is label. Okay. So actually, what we can do now is take the shuffled label, like we saw up here, right? We did birth weight and shuffled label, and so now we can do label and shuffle label. Okay, so what I said before was you can select out just the shuffle label and the birth weights column, but in this case, you actually don't have to because we wrote this difference of means function to like take into account just that birth weights column and the shuffle labels. Yeah, so the function that you write won't always follow the same pattern. Sometimes you might want to drop a column. Sometimes you might want to keep the column. It depends on like what the question is asking in the specific situation. But yeah, this is a really common way we can do A/B testing. We'll shuffle the labels. We'll add those shuffle labels back into our shuffle table, and then we're going to take that test statistic function that we defined above and use our shuffle table and like our shuffled labels in order to calculate that. Okay, so now we have our one simulated difference, which will simulate one trial for us and calculate a test statistic for us. So let's do that. One simulated difference, and we're going to be using the births table. Our label of numerical values is going to be birth, weight, and then our label for the group is going to be maternal smoker. And now we have one simulated difference. And now we can run this many times. You can see we're getting a lot of values that are like -1, 1, etc. So it seems like -9 isn't really showing up, but let's just do this many times just to see. So what we're going to do is first, we're going to be doing, let's just call this differences. Make that an empty array. And now we want to do this 2,500 times, right? So what should we do now? Yeah, exactly. Let's do a for loop. For I in mp.arange 2,500, what we're going to be doing. So what are we doing in each iteration of the for loop? Yeah, we're appending. And what value are we appending? Yeah, so let's do one simulated value. And we're going to be doing this function that we had above, right? And then now we want to append to differences. So remember to use this differences equals mp.append. We're appending to differences. And we're appending one simulated value. So this might take a long time to run. Let's do differences here. Okay, so in the meantime, let's just sum up again what we did so far. So we had an original table called births. Let me scroll back up. So we had an original table called births. We took the maternal smoker and birth weight columns from that table. And now we want to do a hypothesis test and say, okay, under the null hypothesis, so under the null hypothesis, we're saying, okay, they come from the same underlying distribution. So it wouldn't matter if the mother was a smoker or non-smoker, those birth weights would all be like coming from the same distribution. So those labels don't matter, so we can just shuffle that. So that's what we're doing. We're shuffling those labels and adding those shuffle labels back into our original table. And then we can do our test statistic on that shuffle table and calculate the difference in means. And we're expecting that to be around 0, but maybe like a little bit plus or minus like 2 or 3 maybe. but our observed difference was -9. So let's see exactly like how different that is. So we want to do that by doing a permutation test. So what we're doing is we're sampling with replacement and taking that column of group labels so that you have all those shuffled labels. You're adding that back into the original table, and then you're taking the test statistic, which in this case is the difference of averages. But of course, your test statistic can be different. This is just one example of a test statistic. And so we can do that whole process 2,500 times. Okay, I'm going to pause for questions. Yeah, so in this example, the label is the birth weights and the group label is the smoker non-smoker, which we'll be calling maternal smoker. Yeah, the permutation is just how we shuffle the labels. So that's just what we're calling the shuffle labels part. Yeah, it does matter if you subtract A from B or B from A. So let's scroll back up to this grouping part. So actually something that's a little bit interesting about grouping is when you group, it actually puts it into alphabetical order for you. So that's why we see false first and then true second. And that's why we'll always see like false first and then true second, because that's what we're, yeah. So we'll always see false first and true second. And so that's why we're always subtracting like item 1 minus item 0, because we want the mothers who did smoke minus the mothers who didn't smoke in this case. You can also, so if you're asking if the test statistic could also be the mothers who, like the opposite way around, so group B minus group A or group A minus group B, both of those test statistics work, but you have to make sure that that stays consistent throughout the whole hypothesis test. Okay, so this is actually taking a while. Are there any other questions? Okay, I'm actually going to sum this up while we let that run. My apologies, I should have chosen a smaller number of trials. But yeah, let's just go over the whole A/B testing thing one more time. So the most important thing to remember from today is that A/B tests are hypothesis tests. It's just a specific type of hypothesis test. So you're doing all of the same steps. It's just some of the steps are a little bit different. So you're still determining two models for like two different worldviews for what's happening. You have your null hypothesis and the alternative hypothesis. But the difference here is that your null hypothesis might be a little bit different, right? So in this case, we said in the population, the distributions of the birth weights of the babies in the two groups are the same. So that's like saying they come from the same underlying distribution. And then we want to determine a test statistic that gives evidence for the alternative model. So that's the same. The only difference is maybe we want a different test statistic that compares the two groups. So in this case, we're doing the difference between group means. So the test statistic and A/B tests are often, but absolutely not always, the difference or absolute difference between group means. And then our next step is to simulate the test statistic under the null hypothesis many times and store those values in an array. So again, that's the same, right? We are still simulating the test statistic under the null hypothesis. The only difference in this case, when we're simulating, we want to simulate by shuffling the labels of the column of the table. And then the last few steps are the same, right? We're comparing the observed test statistic and its empirical distribution under the null hypothesis. So we're comparing that red dot with the histogram, and the histogram's taking a little bit of a longer time to generate right now. But we're still going to be comparing that observed test statistic of -9.2 or something like that, and then to our histogram. And then we're still going to be drawing a conclusion comparing that p-value to the p-value cutoff. Okay, it looks like it generated. Okay, awesome. So now let's add this to the table. So let's do table with column. Let's call this simulated differences. Let's add differences. Sorry, I'm doing this kind of quickly. We want to do a histogram. Okay, so you can see how it looks like most of the differences are between -3 and 3 with like a little bit of variation there, but the value we got was -9, right? So let's calculate that p-value. How many of those are in that left tail? So let's do np.count non-zero. See differences is less than or equal to. Remember, because we're checking that left side, our more negative values are going to be favoring the alternative. So we're doing observed difference. And we want to do that divided by the length of differences. Then what's our p-value? 0. So it turns out, okay, so the probability of actually getting that value isn't going to be 0. It's going to be really, really, really small, but it won't be 0. But in this case, we did 2,500 trials and none of them were -9 point whatever or more extreme than that. So if we compare that to a 1% p-value cutoff, we would reject the null hypothesis. Okay, I know it's past 11, so I think Kenai sent the attendance form in the chat. And it'd be great if you could take the time to fill out the project one feedback. We're not going to be closing the form right away or anything, so you can take a little bit of time to do that. There's no lab assignment tomorrow in section, but you are going over like a lot of practice problems for the midterm. So if you want extra midterm review, it'd be great if you could show up. The code is ABBA because it's A/B test. So I thought A/B was a little too simple. So I did A/B and then B/A, and then I thought ABBA was funny. Okay. Yeah, the p-value computation. So what we're doing here is the p-value is the probability that's in the left tail, right? So we can shift these bins. Actually, let's do bins. Okay, actually do. Okay, so let's say this is our histogram of values and -9 was like all the way over here, right? And so for our p-value, we wanted to calculate the probability under the null that we get our observed value or more extreme. And so in order to get that probability, we want to count up how many of those are observed value or more extreme. And we want to divide that by the total number of simulated values. So that's what we're doing here with this np.count non-zero thing. What we're doing is we're taking all of our simulated values and we're counting up how many of those are less than or equal to what our observed value was. And you could see visually, there aren't any values of the histogram that are like way up to -9 or further than that. So you can say, okay, that's probably 0, but let's just double check with the p-value calculation. So we did our numerator, so that's taking the differences. Here, let me copy this part. So this first part tells you if all of those differences were less than or equal to our observed difference. So most of these values are false. And then we're counting all of that up, and then we're dividing by the length of our array, which is 2,500, and we get a p-value of 0. So the last lecture that will be in scope for the midterm will actually be tomorrow on causality. But A/B testing is a pretty big concept that is in scope for your midterm. So I would take the time to kind of practice this on your own. So the p-value cutoff, I just determined it to be 1%, but you can decide for yourself if the problem allows you to, and you should decide that at the beginning of the problem. Yeah, hopefully this kind of helped step you through a little bit about p-values and A/B testing. Let me stop recording.